It's time for lecture 3, and where I want to go with this lecture is to two places. The first, I want to look at how we get probabilities out of the mathematical framework we're building for quantum mechanics. And then in the second half, what I want to do is come back to the idea of bases for a little bit longer so that we can start to think about how you might implement different types of measurements without having to completely change the vector space. Okay, so just a quick recap of where we are in the course. In the last lecture we started building a mathematical framework, and so what we did was decided that the way we would handle our system is to stop working in the real 3D world where we have up and down and so forth, and basically translate everything across to a n-dimensional complex vector space where the number of dimensions is equal to the number of measurables. So for a quantum spin, it's two possible measurable states up or down for any particular direction we want to orient our magnetic field. And so that means we've got a 2D complex vector space. We call it a Hilbert space. And what we do is we assign the basis vectors for that space to be orthogonal to each other and unit length, and we make them be the measurables for the system. So in the particular case we're considering yesterday, we basically made one up and the other one orthogonal to it is down. And then we have a whole pile of possible vectors in that space that correspond to possible states of the system, where the spin is pointing in some direction that's not quite up and not quite down, but something in between. Okay, and so where I want to go today is, in the first place, how we then take that into executing the kind of measurements that we talked about in the first lecture, where we put a spin into our sort of Qtron instrument for measuring spin alignment. And you'll remember the first experiment we did, we had this spin that was slightly off up, and when we put it in, most of the time we found it was up, and then some of the times we found it pointing down. Okay, and what we'll see today is where that pops out of our mathematical framework so that things start to make sense. So let me bring up some slides. Where we're going to start here is with the concept of probabilities being projections of the state vector onto basis states. I'll talk about projections in a moment, but the first thing I want to start with is the idea that, suppose we want to know the probability of a quantum spin in a state chi s for the moment. Let's just call it some arbitrary state in between. And we want to make the measurement of what is the projection of the spin along the z-axis. Is it up or is it down? Okay, two possible outcomes there. Our two basis states here, you can see up and down. Okay. What we find is something comes out quite simple here, and I'll explain why it comes out like this in a moment, is that we have a thing that we call a probability amplitude, and the probability amplitude is basically just the inner product between the state that you're interested in, or the state of the system you're interested in, and one of the particular basis vectors that you're interested in knowing the outcome of. So imagine we have our Qtron at the start and we set the little arrow to point upwards. What we're interested in is measuring what the sort of alignment of that spin is relative to that direction, whether it's up a +1 or down a -1. And so what we do then is just take the inner product of that particular state with the state that we're interested in measuring, which is our basis state, and that will give us what we call a probability amplitude. I'll explain why it's a probability amplitude, not a probability, in a moment. Okay, but just imagine I was interested instead in having the arrow pointing downwards, and you'll remember we did this in the first lecture. We had the arrow pointing downwards and we put a spin up in, and we got a -1 instead of a +1 because the spin is pointing in the opposite direction to that direction we chose. And so in that particular case here, you would take the inner product between the down basis state and the state vector for the system. Okay, so the state of the system, you're going to start hearing me use the word state vector a lot from here forwards, and really what I'm just referring to is the vector of the state of the system before we do a measurement. Okay. Alright, so the important thing to keep in mind here is that probability is not probability amplitude. And what the probability is it's actually the product of the probability amplitude, which is this number we get up here, and its complex conjugate, which, if you remember back to the last lecture, if you take an inner product and you take the complex conjugate, it's basically the equivalent thing to reversing the order of the two operators, okay? The reason we do this is because, again, we come back to this visualization challenge. What we're doing here is in a 2D plane, we're actually representing a 2D complex vector space. And so all of the vectors that I draw here actually have a complex amplitude to them, right? Some of you hopefully have been thinking about how to make sense of this thing and thinking, oh, you know, I've got a 2D space and then I've got a complex. So each of those two dimensions must have two dimensions itself because there's a real and an imaginary plane. And so maybe I've just got a four-dimensional space. Doesn't quite work like that. It's not explicitly like a four-dimensional real vector space. Otherwise, what we would probably do is use a 4D real vector space instead of a 2D complex vector space. Those two things are not equivalent things. 4D real vector space is not a 2D complex vector space, okay? So there's subtle difference between the two, and if you try to do quantum mechanics in a 4D real vector space, you find out also that you get wrong answers. Your mathematical framework just does not match your experiments. So what's going on here is that whenever I draw one of these diagrams, what I'm doing is kind of cheating the system a little bit. I'm in a 2D space with a whole pile of vectors that can have complex amplitudes to them. And I just happen to be very conveniently choosing the ones that are complex numbers where the imaginary part is 0. Okay, so whether it's up or down or left or right, all of them have their amplitude such that the imaginary component of that amplitude is 0. And so I can basically reduce them down into this 2D plane that I'm drawing in here, okay? So again, visualizing these systems gets very tricky, and later on in this lecture we'll look at the in and out directions where the amplitudes actually become complex, and you'll find that I just won't draw any Hilbert spaces for those because I don't know how to draw them, okay? There's no way I can physically represent them on a 2D page. Okay, so in a lot of the cases that we do here that are very simple with up, down, and sort of superpositions of up and down, you don't see that complex amplitude, but that complex amplitude still exists. And so when you take the inner product, what you're getting is a scalar, but that scalar can be a complex number. It's not necessarily a real number just by taking that dot product, okay? And as you know, probabilities have to be real. You can't say the probability of me tossing a coin or the probability of me winning the lottery is imaginary. Well, actually, probability of me winning the lotto probably is imaginary because my luck's not great. But any probability that we have is a real number, okay? And so what we need to do is make sure that out of this mathematical framework we have, things that pop out of it in terms of probabilities are real. And so the way we do that is we know if we take any complex number and multiply it by its complex conjugate, it becomes a real number, right? We basically cancel out the two imaginary parts. And so the way this theory is designed, and it's, I mean, again, we come back to this question, is designed this way because it is the way it works and explains experiments that we see in the real world, is that the probability is not the inner product on its own, it's the inner product times its conjugate to convert it back into a real number, okay? Some of you who may have done a little bit more quantum mechanics than others will probably see the connection here if you've done wave functions before. There you learn that the wave function itself is this equivalent of a probability amplitude. It's a complex function. And what you do is you multiply the wave function by its complex conjugate, you get this psi star psi thing, and that actually gives you probability or probability density, okay? We'll come back and talk about that a little bit later. All right, so what we're really doing in here is going, I'm going to take the inner product and I'm going to multiply it by its complex conjugate, all right? And as you know, that's the equivalent thing to reversing the order of the Bra and Ket in that particular case. And so what we can do here for this particular state chi s is calculate what the probability of the spin being up is by basically taking the product of the sort of the product of the inner product of U and chi-s and the conjugate, okay? And if we want to do this, if we want to find out what the probability of down is, we would do the same thing, except now we would insert the basis state down instead of the basis state up, okay? Now I've written this in a very specific way, and the order of these two operators that I've written here really matters in the end. And it matters because of the way we think about, I mean, it doesn't matter in terms of what the outcome is, it matters in terms of what the way we think about putting bracket notation together. Okay, so for example, imagine this number here is a complex number. I multiply it by its complex conjugate. It doesn't really matter which way I multiply a complex number and its complex conjugate, I will still get the same answer. As you know, complex numbers obey commutativity. Okay, so this is not a commutativity issue right here. What it is that usually what I do is put states of the systems in bracket notation as the two vectors on the end, the ket and the bra, because that's sort of naturally where they go. And what goes in the middle here is usually things that we call operators, okay? We'll talk about operators more in the next lecture, but I just want to point this out for a second here. This thing in here is what we would call an operator, and we tend to call it a projection operator. In a second I'll explain what projection is, but we call it a projection operator because basically what it does is do a projection. This thing in the middle here is, you'll know from yesterday's lecture, this thing up here is what we call a inner product, and it's basically sort of like a product of two vectors that gives you a scalar, okay? This thing in here is what we basically call an outer product, and what we're doing there is we're multiplying a vector by a vector, but the way we multiply these together is not such that they reduce down to a scalar, but so that if you've got a two-element row vector and a two-element column vector, when you multiply these two things, they become a 2 by 2 matrix, okay? So this thing in the middle here becomes a matrix, which is then what we call an operator in quantum mechanics, and I'll talk about that next lecture, okay? And you can see that this is basically a projection operator for up. This thing in here is what we call a projection operator for down. And if you want to find the probability of a particular state being measured as a particular measurable outcome, all you do is basically put the state on the left, state on the right, the corresponding projection operator for whatever basis vector you're interested in measuring in the middle, and out pops the probability, okay? Something I'll point out here, and again I'll come back to this in the next lecture, is that if I just consider this to be an operator, I've got a ket, I've got a bra, I've got an operator, I've got a ket, and what I'm really doing here is calculating an expectation value. Okay, so what I'm really doing here is just asking what is the expectation value for a measurement in this particular case. All right, we'll come back to expectation values in the next lecture. So let's just pop back to probability amplitude again for a moment, because I want to explain why we use the word projection. Those of you who might have done subjects like engineering drawing or sort of, you know, architecture or technical drawing in high school or other subjects may automatically know what I mean by projection, because for me it's kind of a native thing since I did technical drawing in high school. What this inner product is here really, and we talked about this in the last lecture, it's basically the dot product of our state vector and the basis vector of interest. And when we think about that, what we're really doing is we're taking the product of the length of the basis vector, which of course, because it's a basis vector, it's 1, right? This is the main reason why we like orthonormal basis. That is 1, and so the only thing that carries into the amplitude is the length of the state vector, okay? Which is also 1, right? So really in here we've got 1 times 1 is 1. Then we've got cos of the angle in between. So what we're really looking at as probabilities here is something that's dependent on where this vector sits in terms of its angle relative to the basis vector that you're interested in using for the measurement, okay? And so here what you see is that this vector is kind of symmetric between up and down. That's why we call it chi-s for chi-symmetric. It's a 50% mix of up and down as a possibility. And you can imagine if we brought this vector round on this unit circle over to here somewhere, it's going to be a little more up than down. And so, correspondingly, the length of, or the magnitude of that product is going to be larger than it will be in the other direction. Okay. Now, if we plug this through, we know that the unit vector is 1. We know that chi-s, if everything's normalized, should be 1 as well. We end up with chi-s cos phi. And if you look at what chi-s cos phi really is down here, it's this little green arrow that you see running along this up vector direction. Okay. And in particular, you can basically draw a line, this orange dashed line here, perpendicular. This thing is really just the component, in first year physics terms, it's the component of the vector chi-s onto the u vector direction. If you think about it in terms of, the way you draw things, this is really just a projection of the chi-s vector onto the u-axis, okay? So projection ends up being the winning out term over component in this particular case, which is why I'm having to explain what a projection is. They're the same thing ultimately. But what we're really doing here is basically just looking at what the projection of this vector onto that axis is, and that is the probability. Okay? And this is why we talk about, why you will hear in quantum mechanics and you'll see in the textbooks, projective measurement or probabilities as projections, right? You're basically just taking a state and projecting it onto an axis. Okay. So if we go to the next slide, what I want to do now is I want to walk you through an example here, just so that we see what the maths looks like, and it's a fairly simple one. And I'm going to do it just for this symmetric state, just in here. So this symmetric state, as we saw in yesterday's lecture, it's essentially a 50-50 mix of up and down. We'll show in the second half that it's actually a state pointing to the right. And if you normalize this thing so that the unit vector has a length 1, then basically you're writing a column vector that's got 1 over square root 2 on the top and 1 over square root 2 in the bottom. Okay? If you want to check that this thing is normalized, I'm not going to do it because it's kind of trivial. But you can do it for yourself. You just want to take the inner product of that vector with its corresponding bra and work that through, and you should find the answer is 1. Okay? I'll let you verify that for yourself. Okay, so I'm going to do the probability 2 ways here. The first way, I'm going to do it with the sort of inner product idea that I talked about on the last slide. And it's kind of simple and quick and easy. And then after that, what I'm going to do is show you the projection operator version of it. And I'm going to do that more so that I set up later on for operators in the next lecture. But also, sometimes it's good to have alternatives for how you calculate things. So that, I always used to try to have fallbacks for things as an undergraduate student, more than one way to calculate things, so that if all of a sudden in an exam I found either it wasn't working or I couldn't remember some bit of it, I had some other way to attack the problem. Okay, so I'm going to show you both. There's lots of little ways to calculate probabilities in quantum mechanics, and if you look at the different books, they all like different sorts of notation. Okay, so what we're going to do is take this symmetric state, and we're going to try and calculate the probability of putting that into a measurement and getting a spin pointing upwards, right? And we know that, if we have a state that's halfway between up and down, 50% of the time we should find it up and 50% of the time we should find it down, okay, from the first lecture. So we're kind of expecting a probability of a half here. Okay, so what we're going to do here is calculate the probability of getting a spin up. And so this thing is going to be the probability amplitude for up conjugate times the probability amplitude for up. And we can get this probability amplitude for up just as the inner product of u and chi-s, okay? And so our state up here is 1, 0. As I said before, I'll add the conjugates in just so that we're really clear on what's going on. Here it'll be 1 over root 2 and 1 over root 2. And then I can go through and just do this multiplication, right? So it's going to be 1 times 1 over root 2 plus 0 times 1 over root 2. So this is just going to be 1 over root 2, okay? So then if I think here in terms of the conjugate of my probability amplitude, the conjugate of 1 over root 2 is just 1 over root 2 because it's a real number already. And then the probability amplitude here is just 1 over root 2. Multiply those two things together and I get a half, okay? If I want to get the probability of a downstate here, I could either do exactly what I just did again, but using the down vector. So all I would be doing is swapping the 1 and 0, and you can already see here that if I swap the 1 and 0, all I'm going to get is 0 times 1 over root 2 plus 1 times 1 over root 2, which is 1 over root 2, and the whole thing ends up being a half. The other way that sometimes is a nice shortcut is, particularly if you've got two possible outcomes, is if you know the probability of one, you automatically know the probability of the other because there's only two and they have to add to one, right? And so this is a trick that if you're savvy in exams, it's perfectly okay to use, and I'm always surprised how few students do it, is just to go, this is 1 minus pu, and so it's going to be 1 minus a half, and so this thing here will be a half. Okay, so we've got a probability of a half of it being up, a probability of a half of it being down. Okay, so that's one version of it. Perfectly acceptable way to do it. And the other way I'm going to do it now is by setting up what I called on the last slide, the projection operator. So now what we'll be doing is probability of u is chi-s as the ket on the right, and in between what I'm going to have is the projection operator u, okay? So the first step in here, I'm just going to show you what an outer product looks like. So this outer product here, u, looks like this. And so what I'd be doing here is going sorry, it's the wrong way around. The ket's on the left, so it's the column vector, 1, 0, and the bra is on the right, so it's the row vector, and so these would have conjugates in it, of course, okay? And now I would go through and work out what the corresponding 2 by 2 matrix is, okay? And so the first element times the first element is the top corner, so 1 times 1 is 1. The next one over is the top element times the one on the right, so it's 1 times 0 is 0. The bottom left element is the bottom element and the left element, so 0 times 1 is 0. And then the bottom right corner is the bottom element and the right element, so that 0 times 0 is 0, okay? And so this is my way of basically just building from row and column vectors to a matrix, is just go top and right, top and left is top left, top and right is top right, bottom and left is bottom left, and bottom and right is bottom right, okay? Really easy to do. I built myself a matrix here, okay? And so as you'll see in the next lecture, all operators are matrices, and so really all we're doing is just sticking a matrix in between a bra and a ket. So let's do this now as a proper sort of formal thing. Our bra for chi-s is now going to be a row vector, 1 over root 2. Put the conjugate in there just for being pedantic, like so. And then we're going to put our matrix in the middle, 1, 0, 0, 0 in here. And then the last thing we're going to do here is have our column vector, which is our ket chi-s, 1 on root 2, 1 on root 2, like so, okay? And now we can just basically work our way through. So there's nothing stopping which order you do this in. You can take the bra on the left and multiply it by the matrix to get yourself a new vector, and then multiply the new vector by the ket on the right. You can do that. I find that harder to do, sort of just intuitively. I prefer to go the other way. So what I do is I take the matrix and act it on the ket on the right to get myself a new column vector, and then I just multiply the row vector by the column vector. So let's do it that way. So this will now be 1 over root 2, 1 over root 2. And then matrix times vector, basically what you do is you take the row and you multiply it by the column. Okay, and this is why I always like to do it this way, because I have this nice little rule in my head that just goes row by column, row by column, row by column, gives you the individual rows of your vector. So it would be 1 times 1 over root 2 plus 0 times 1 over root 2 is 1 over root 2. And then the bottom row of the matrix is 0 and 0. So it's 0 times 1 over root 2 plus 0 times 1 over root 2 is 0, of course. Like so, right? And now I just do a multiplication between the row vector and the column vector. So it's 1 over root 2 times 1 over root 2 plus 1 over root 2 times 0. So that's just going to give me a half, which is exactly the answer I got before, okay? Some of you will be going, well, hang on, this projection operator thing just looks like more algebra on the page to do the same job that he did with probability amplitudes at the top. And that's a fair point. Entirely up to you which of the two you want to use. It's good to be aware of both, just because sometimes you actually do want to build operators in much this way using outer products, right? And it's also very easy to remember where the probability comes from when you know that all you really have to do is just stick the two state vectors on the end of whatever your projection operator of interest is and work your way through the problem. Okay, so choose whichever one seems easier or more familiar to you, but it's a good idea to know both because it's a good safety net for when you're working through problems. Okay, now with that done, there's one little point I want to make before I jump off this slide, which is that once you take the projection of this particular vector here along this u direction, you get an answer out here, which is now your projected probability of getting an outcome for that measurement, right? One thing that you find is that once you've done that, there's absolutely no way of going back to the original vector. And the reason why there's no way of going back to the original vector is because there's other possible vectors in the space that will give you the same answer from the projection, right? Now, again, this comes down to the limitation of being able to show a 2D complex vector space on a page. There's more than 2 vectors for this, but I can only show you 2 really obvious ones right here, right? So there's this one, which will give you exactly this projection you see with the green arrow. But there's also this one here, right? You can imagine there's another chi-s here that is actually up minus down rather than up plus down. And so if you took the projection of that, you would get this green vector too. You can uniquely go from the orange vector to the green vector, but you can't uniquely go from the green vector back to the orange one because you don't know whether you came from the one at the top or you came from the one at the bottom, okay? If you now extend this out fully into a complex vector space, what you realize is that there's actually an infinite number of vectors that correspond to this problem. And so what you're really doing when you do this projection is the equivalent of what you might hear discussed in quantum mechanics quite a bit of collapsing the wave function or collapsing the state of the system, right? What you're really doing by taking the measurement is taking some arbitrary state vector, projecting it onto some axis so that you can work out the probability, and then at that point your ability to go back uniquely to a vector is gone because there's a whole pile of vectors that can give you that projection, okay? I actually prefer to not think about this much anymore as collapse of the wave function and more to see it instead as just something that's part of measurement being an invasive process, right? Measurement changes the state, and it changes the state because you basically have to project onto a basis vector in order to do the measurement. Okay, so I'm not going to go into this one too deeply. The probability of outcome for an arbitrary state then just follows in exactly the same way, okay? And so you can imagine having some arbitrary vector here, and of course it would be some superposition of up and down. And the prefactors here won't be as simple as the symmetric state on the last slide. They might be, you know, some number larger than 1 over root 2 and some number smaller than 1 over root 2. And there may be minus, there may be a plus, they may even be complex, right? What we do in order to make sure this vector has unit length is make sure that it obeys normalization. And what we mean by that is basically that the relationship that we've got here holds. One way to see this is basically if you take this expression here for chi in this form, and what you do is you look at the norm of it. So you basically take the inner product of that vector with itself, and I'll let you do this for yourself as an exercise. What you'll find is when you do that inner product, you will basically get this, and in order for that vector to be normalized, that thing has to be equal to 1. Okay, so this is what we call like a normalization for a state vector. It's basically just making sure the prefactors obey the fact that it has unit length, so that it's a well-behaved vector in a Hilbert space. Okay, you can now go through and project this vector onto this axis. And you can kind of, if you think back to the first lecture, you can kind of think about this state here as being the state where the spin was, you know, some arbitrary direction that was a little closer to up than down. And most of the time you measured up, and then every so often you measured it down. And you can see this here, right? If you worked out what the projection of this state vector onto the up axis would be, it's quite a long projection. If you now project this onto the down axis, it's quite a short projection. And so the probability of it being up is higher than the probability of it being down. And so if you took this state, and you could make this state again and again and again, because once you have that state and you do the measurement, it goes from being whatever it is to up, right? That projection collapses the state, or it's an invasive measurement. But imagine you could make a million quantum spins, all of which were in this particular state. Then what you would find is you mostly get up. You get up, down, 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 up, right? You'd have a higher probability of getting ups than downs, and this all works out, okay? So I think I'm going to stop here with this idea. I'll let you play with it yourself. It's actually kind of simple once you get the hang of it. You're really just calculating probabilities of outcomes based on looking at either projection operators or inner products for a given state vector for the system relative to what it is you want to measure, okay? After the break, I'm going to come back and talk a little bit more about bases and measurements, and I'll see you in a few moments.